The question reads, a spring of force constant 800 Newton per meter has an extension of 5 centimeter. The work done in extending it from 5 centimeter to 15 centimeter is. For the solution, writing the given data, K equals 800 Newton per meter and the change in the length, that is dx, is equal to 0.05 meter. The starting length is x1 equals 0.05 meter and the end length is x2 equals 0.15 meter. The work done can be written as force into displacement, which can be written as kx into dx, as kx represents the force and dx represents the displacement. So the work can be written as k into the integration of x dx within the limits 0.05 to 0.15, which gives us 800, which is the value for k, and the integration of x gives us x square by 2. Now applying the limits, we get 400 into 0.15 square minus 0.05 squares. Simplifying that, we are going to get a result as 8 joules. A wire fixed at the upper end stretches by a length L by applying a force F. The work done in stretching is. We know that the work done is equal to the change in the potential energy, and the potential energy on a stretched wire is given as half stress into strain into the volume. Substituting for stress, strain and volume, as stress can be written as force by area, strain can be given as the change in length to the length, and the volume can be written as area multiplied by the length. On simplifying, we get the answer as FL divided by 2. Two wires are made up of same material and have the same volume. However, the wire 1 has a cross-sectional area of A and the wire 2 has a cross-sectional area of 3A. If the length of the wire 1 increases by delta x on applying a force F, how much force is needed to stretch the wire 2 by the same amount? Two wires are made up of same material means they have the same Young's modulus. Also, the volume is given as same, means the wire 2 will have 3 times the area, but at the same time it will have 1/3 the length. For wire 1, we can write the Young's modulus as F divided by A divided by delta x by L. Similarly, for the wire 2, we can write Young's modulus as F dash by 3 times of A whole divided by delta x divided by L divided by 3. Since the Young's modulus is same for both the wires, we can equate the two equations. So we get F divided by A into L divided by delta x equals F dash divided by 3A into L divided by 3 into delta x. On simplifying, we are going to get the answer as F dash equals 9 times of F. The pressure that has to be applied to the ends of a steel wire of length 10 cm to keep its length constant when its temperature is raised by 100 degrees Celsius is. Given values for the Young's modulus of steel is 2 into 10 power 11 Newton per meter square, and the coefficient of thermal expansion is given as 1.1 into 10 power minus 5 per Kelvin. We know that the Young's modulus is the ratio of stress to strain, which can be rewritten as stress equals Young's modulus multiplied by the strain. Also, the pressure is equal to stress. So we can write pressure equal to stress equals Y, that is the Young's modulus times the strain. Also, we know that the thermal strain is given as change in length to the length. That can be written as alpha times delta T, where alpha is the coefficient of linear expansion and delta T is the change in temperature. As the length needs to remain constant, we can substitute the values in the equation for the pressure, as Young's modulus is given as 2 into 10 power 11, the coefficient of thermal expansion is given as 1.1 into 10 power minus 5, and the temperature variation is 100. So we can simplify the equation and we can get the result as 2.2 into 10 power 8 Pascal.